So let's take a look at the first example problem for the Centroids and Moments of Inertia lecture. Here, the first problem that we're going to look at is a shape that's defined by boundaries with the y-axis, with this parabola, and then with a horizontal line here at 1 inch above the x-axis. So for this shape, we're asked to find the area, the location of the centroid, the geometric centroid of the shape, the moment of inertia about the x-axis, the moment of inertia about the y-axis, the polar moment of inertia j, and the radius of gyration about the x-axis r sub x. So this is a shape that we're going to want to use integration and the calculus-based formulas to solve for all these values as kind of a showcase of how to use that. Now, technically speaking, we could figure out some of these values using the tables that are provided on the formula sheet or in the appendix in the back of your book. We would relatively easily be able to find area and location of the centroid, but it's going to break down at that point. We won't have the formulas for Ix and Iy. So we're going to go through the entire problem using those calculus definitions of area, centroid, moment of inertia, etc. So let's take a look at this and kind of go through it one by one. Part A, it's asking for the area. And so we have a formula in the lecture notes and in your book as well too, that the area is simply the integral over the entire area of dA. That's a very general formula. It's basically saying we're going to take every small little differential area for the entire shape, we're going to add them all together. Now, that doesn't give us a lot to work with, so we're actually going to break this down and simply look at it in terms of taking either vertical slices through this area or horizontal slices and adding up all of the areas for each of those slices independently. So we could say the integral over the entire area of y times dx, or we could look at the other axis and we could say the integral over the area of x times dy. And just to get a little sketch of what we're talking about here, if in this case I'm looking at the vertical height y times dx, we're talking about taking the shape like this, taking a small slice of it, dx, and that width times the height, which is going to be called y in this case, if I add up all the areas of those slices across the entire length of this parabolic shape, I add them all up and I'll get the full area. The alternative would be to look at the same shape, but to take a horizontal slice. And so in this case, the slice that we're looking at has a height of dy, some differential thickness, and then the x distance that we're talking about is just that horizontal width of that slice. So either of these approaches will work. The things that you need to be careful about is here our formula says y times dx. Y is simply the height of that section, that slice, at our location of dx. It's not talking about the y-coordinate of here, the y-coordinate of here. It's talking about the difference between them. The same thing over here. X is simply referring to the width of that slice. And when we start looking at functions like this, we're not necessarily talking about this y and this x. So you just need to be careful about that. Here, when we're talking about y, we're really talking about I'll just say the height of the shape at dx, and here with x we're really talking about the width at dy. And we'll see why that's important here in just a second. So let's just go ahead and we'll start out doing the vertical slice, and then we'll do the same thing with the horizontal slice. So again, area equals the integral over the entire area of y times dx. So if we're looking at our shape over here, we're talking about a vertical slice through it And this vertical slice has a width of dx. And so now we need to define what is the height, this y value, as a function of x. And so we can pretty quickly define the height of this by figuring out what is the function of the top of this parabolic area, what is the function of the bottom. So one thing that we might want to do really quickly is figure out what is the equation of the top line of this shape. And here it has a constant value of y equals 1 inch. So the function is really easy. Y just equals 1. The function for the parabola is a little bit trickier, but we're given the formula already. All that we want to do is simply rewrite this in terms of y by itself. So when we do that, you can see that the height of this slice at any given value of x is simply equal to 1 minus this value. And so we can say that the height simply equals the function on the top, 1 minus the function on the bottom, which is x squared over 4. Now we have everything that we need to be able to integrate this. The lower and the upper bound will be a little bit tricky as well too. Here at the far left side we have x is equal to 0. At the far right side at the end of our area we have x is equal to 2 inches. So we're really talking about x from 0 inches to 2 inches of y, and we calculated that as this 1 minus x squared over 4 dx. And then this is simply power rule, right? If I just look at this, it's a polynomial, and I will get x minus x cubed divided by 12, and that'll be evaluated at x equals 2 inches and at x equals 0. And so simply I'm going to get 2 minus 2 cubed divided by 12, and then simply minus 0. If I plug in 0 here, I get 0 minus 0, not a big deal. And here I end up with 1.333 inches squared. So there's my area right there, 1.333 inches squared. I did leave out the units in here, but if you were to follow through with the units in your integration, you would find that you do get inches squared as a result. Okay, so let's redo this. I'm going to go ahead and put a placeholder here. I'm going to identify that we've calculated the area as 1.33 inches squared. And let's just go ahead and redo it by taking a horizontal slice instead and make sure that we still get the same value. So there might be some strategy in which type of a slice you take. One might be easier than the other. But the bad news, well, not bad news, but oftentimes to get to these next values like centroid, you're still going to have to take a horizontal or a vertical slice. There are some tricky ways to get around it, but you need to be comfortable with either horizontal slices or vertical slices. So let's just go ahead and rewrite our equation as equal to the integral of x dy. Let's go ahead and draw our figure again. And so now we're talking about a differential vertical slice with a height of dy. And so I need to be able to figure out what is my value of x, or in other words, what is the width of this slice right here. And then I'll go ahead and integrate them over the entire area. So looking at this, I need to be able to relate or figure out this width right here as a function of y. So all that I need to do is I simply need to rewrite this equation here to solve for it in terms of x. So I do a little bit of algebra, and I get that x is equal to 2 times y to the 0.5 power. I bring 4 over here, I take the square root of both sides, and I get square root of 4 times square root of y. I can simplify it a little bit down and get 2 times y to the 0.5 power. Once I've done that, I now have my function for x. X simply equals 2y to the 0.5. And now I want to look at my upper and lower limits for my integration. I'm integrating over the entire area, and that means I need to start right here at y is equal to 0. And then as I go up, I will end right here where y is equal to 1 inch. So with that in mind, I just need to plug in my values into my function for area now. Area equals the integral from y equals 0 inches to 1 inch. And my function for the width right here is simply 2y to the 0.5. And the integral is taken with respect to y. So if I do this, again, it's still a relatively simple power rule. I'm simply going to get 2 times y to the 1.5 divided by 1.5, evaluated at 1 inch and evaluated at 0. And I get 2 times 1 inch to the 1.5. I'm actually just going to leave units out of here because I've already not included them for some other parts. So let's put in 2 times 1 to the 1.5 divided by 1.5 and then minus. If I plug in 0 here, I'll just get a term of 0. And I simply get 2 divided by 1.5 equals 1.333. And now I'll put the units on because I left them out of the integral. As long as everything is in the same consistent units, I don't need to worry about unit conversion. And so it's not as important to track through the units here. 1.333 square inches is exactly what I got using the opposite method where I'm taking a vertical slice as opposed to a horizontal slice. Okay, so that's part A, the area. 2 different ways to calculate it, and in fact, we could even change this diagram even more, be even trickier about it, but these are 2 relatively simple ways to go about it. The easiest places to make a mistake is in how we define x and y in our area equation. Remember, we're talking about the width of whatever slice you're taking or the height of whatever slice you're taking, and that's why it can be a little bit tricky. Okay, so next, let's talk about part B. So part B is the centroid. And I'll put that down as x sub c, comma, y sub c. We're talking about what are the coordinates, the x and the y coordinate of this location here, the geometric center of this shape. And we have a relatively simple equation for that, and we've already calculated half of this, as you'll see in a second. It's equal to the integral over the area of x times dA over the integral over the area of dA. Now this is simply saying the first moment of area divided by the area. And so it's saying for any little differential area here, the numerator, I will multiply this little area times its distance from the y-axis. That's the numerator, and I add up all those results. For the denominator, it's simply adding up the areas themselves. I've already calculated the denominator. It's already 1.333 square inches. So now I need like this weighted average is basically what we're doing. So to do that, I need to go back and do a slice. That's the easiest way for us to break down these small differential areas into more kind of manageable chunks. And so here we're interested in the x distance, and even though there's multiple ways to do this, I think that the most simple way to do it would be another vertical slice here. It has a width of dx, and the area will simply be dx times this height. And again, Based off the formula, we just simply call the height of this is equal to y. But we already calculated that earlier as simply equal to 1 minus y squared, or sorry, 1 minus x squared divided by 4. That was from part A when we first looked at it. I can define the height of this, which is really what y is talking about, as this function on top, y equals 1, minus the bottom, which is x squared divided by 4. So if we do that, all that we have to do is take this area, which is dx times y, which is this function, and multiply it times x. So just to make that as explicit as possible, I'm talking about an integral of x times y dx divided by the total area. We just happen to calculate what that height is here as 1 minus x squared divided by 4. So to make this just a little bit more clear, we're talking about the integral of x times 1 minus x squared divided by 4 dx divided by 1.333 inches squared. So I do a little bit of calculus here, and I get the integral of x minus x cubed divided by 4 dx over 1.333 square inches. And then this is the limits of this integration we haven't talked about yet. We need to put those in as well. So I start on the left side where x equals 0, and I end on the right side where x is equal to 2 inches. So this is really from 0 to 2. And so finally I get x squared divided by 2 minus x to the 4th divided by 16, evaluated at 0 and 2, and then finally divided by 1.333 inches squared. Now, it might not be obvious because we haven't been tracking through with the units in our integration here, but the units on top are going to be in units of inches cubed. The denominator will be inches squared, which is why we end up with inches as our final answer. Now, if I plug in my numbers to get the value for this, I get, okay, this is x sub c. I get that x sub c is equal to 0.750 inches. All that I'm doing for that is just plugging in x equals 2 here, dividing it by 1.333, and then I get 0.75 inches. So let's just go ahead and make sure that this makes sense. It passes kind of the smell test. So obviously the centroid has to be in between the two extreme x values of the shape. So between 0 and 2, so first check, we're good to go. 0.75 is between 0 and 2. Now if this was a rectangle, we know that the centroid would be right at half width, right at x equals 1. But because this isn't a rectangle and more of the area is on the left-hand side, it should be less than 1. And again, that checks out 0.75. And so here, the centroid should be left of center, which is what we see. So far so good. For x sub c, we get 0.750 inches. Now, as you can imagine, the process for the y sub c coordinate is very much the same. And so we're just going to go ahead and look at that. Like I said, there are multiple different ways to take this slice and kind of define what your differential area looks like. But we're just going to do another example where y sub c again equals the integral over the area of y dA over just the area itself. And so if we take a look at our parabolic area again, what we care about is the vertical distance here. So I'm going to have y, and now we're going to make a horizontal slice. It has a differential thickness dy, and so in order to turn that into dA, in order to get the differential area of this slice right here, it's simply equal to the thickness dy times whatever this width is, and we're just calling that x. And we calculated that earlier we simply said that x is equal to 2y to the 0.5 power. And so now I have everything. dA is simply dy times 2y to the 0.5, and then times this distance y in order to turn it into a weighted area. So really all that I'm doing here is the integral, and let's talk about the limits here. The bottom is y equals 0, the top is y equals 1 inch. And so I go from 0 to 1 of y times 2y to the 0.5 power dy, and then divided by 1.333 square inches, because that's what we got from part A. And if I go ahead and evaluate that, again, it's still just the power rule, and I get yc equals the integral from 0 to 1 of 2 times y to the 1.5 power dy divided by 1.333 square inches. So all that I've done at this step is simply multiply y times 2y to the 0.5 power, combine them into a single term, and so when I do power rule, I get 2y to the 2.5 power divided by 2.5, the whole thing divided by 1.333 square inches, the top evaluated at 0 and 1. So all I need to do at this point is plug in 1 for y. If I plug in 0, I'm going to get 0 for the full answer. So I plug in 1 here, I get 2 times 1 to the 2.5 powers is 2, divided by 2.5, divided by 1.333. So if I do that, I get that y sub c equals 0.60 inches. So let's do the same thing. Let's go ahead and check our work, make sure that it's reasonable. So obviously the centroid of this shape has to be between the two extremes, which is y equals 0, y equals 1. So y equals 0.6 makes sense. If this was a rectangle, y sub c would be half the height, or 0.5. Obviously this is not a rectangle. More of the area is weighted towards the top half, which means that my centroid should be above half the height. 0.6 is greater than 0.5, so it passes the smell test. It's reasonable, and so we can feel pretty comfortable about that. 0.60 inches. Now, like I said, there are other ways to slice this. There are other ways to deal with it. You can still get the right answer multiple different ways, but you do need to be comfortable using integration, and you do need to be comfortable kind of making the slice either horizontally or vertically. And I find that graphics, a nice engineering sketch, is going to help out quite a bit. Okay, so let's go ahead and get into the, I wouldn't call it trickier problems, but all that we're doing for the moment of inertia is simply taking, making it a little bit more complex of an integration. But other than that, it's fundamentally really the same kind of an idea. So I'm going to go ahead and erase this. And so the equation that we have for moment of inertia is slightly different. And we'll do moment of inertia about the x-axis first. So our formula is that the moment of inertia about the x-axis is equal to the integral of y squared dA. So if we were to kind of turn this into a schematic and look at what this means, it's that for any little differential area, I need to multiply that area times its distance from the x-axis. And not only its distance from the x-axis, but this term squared. So I take this area, I multiply it times the square of the distance from the x-axis, then I just add up all of those results. So to do that, I need to make, not surprisingly, another sketch. So just like before, there are maybe multiple ways to do this. I'm going to go ahead and draw this a little bit bigger. We have our parabola, and I could choose to make either a vertical slice or a horizontal slice. I think that it makes the most sense to do a horizontal slice here because that's already at our distance of interest, y. And Now I've got my slice here. It has a differential height of dy, and we need to figure out what the width is. Again, commonly just called x, but what we're talking about here in terms of dA equals x times dy, we're talking about x just simply being the width of this shape right here. We've already figured out what x is equal to before. X is simply equal to 2y to the 0.5 power. And so we have kind of everything in this term that we need to figure out what the moment of inertia is, because I simply plug in my equation here for dA right here. Y squared, I'm already defining this as the distance from the x-axis. And so as a result, I get, oh, and we still have our lower bound, which is y equals 0, our upper bound, which is y equals 1. And I get that I sub x, the moment of inertia about the x-axis, is equal to the integral from 0 to 1 of y squared times 2y to the 0.5 power dy. Now I can integrate, I can combine like terms to make life a little bit easier. 0 to 1, and I get 2y to the 2.5 power dy. If I integrate that, I get 2y to the 3.5 power divided by 3.5, evaluated at 0 and 1, and I get Ix equals 0.5714, and this will be in units of inches to the fourth. Inches to the fourth because we're talking about distance squared times an area, which is simply distance squared. So distance squared times distance squared is going to give us distance to the fourth. And again, here it's pretty easy integral. I just plug in 1, so I get 2 times 1 to the 3.5 divided by 3.5. And unfortunately at this point, unlike the area, unlike the centroid, there's not really an easy way for us to kind of check the reasonableness of this value, because we don't really see the moment of inertia here in the same direct way that we see the area and the centroid. So we just need to, we can double check our work is one way to go about it, but we don't have a quick kind of reasonableness check to make sure that it's correct. So let's talk about, let me write this value down right here. Ix equals 0.5714 inches to the fourth. So now let's go ahead and let's do part D. So the moment of inertia about the y-axis. This is part D, I sub y. And I sub y, the equation for this is nearly identical to for Ix. The biggest difference being that we're talking about x squared dA as opposed to y squared dA. But it's the same idea. We're looking at a small differential area and its distance from the y-axis, which would be called like y tilde. And we take this differential area, we multiply it times the square of this distance to our axis of interest, and then we integrate to add up all of those results together. So I will look at another diagram here. We're interested in multiplying times the square of x times the differential area, which I'm going to define by making a vertical cut and having a width of dx and then a height, again we're calling y, but remember this differential area equals dx times y, y simply being the height, which means the value of the top function minus the value of the bottom function. We defined that earlier as 1 minus x squared divided by 4. So I can simply plug that into my equation here. Let's talk about the limits. Because we're talking about the x direction, My starting value would be x equals 0. My finishing value would be x equals 2 inches. So my integral is the integral from 0 to 2 of x squared times dA, dA being 1 minus x squared over 4 dx. Again, these two terms right here simply equal dA. Doing a little bit of calculus, I can simplify this first, which is probably a good idea. 0 to 2 of x squared minus x to the 4th divided by 4 dx. All that I've done is just distribute the x squared into each term of that polynomial, and I get x cubed divided by 3 minus x to the 5th divided by 20, evaluated at 0 and 2. And when I do that, all that I'm doing is plugging in 2 here, get the value, subtract by 0, which isn't going to change anything. And I get I y equals 1.067. And again, the units will still be inches to the 4th. Again, not a good way to check the reasonableness of this, but you could go through and double check your math. This is probably the best way to do it. You could, for a problem like this, potentially try to look up some tables for a parabola, find out what the moments of inertia are. There are going to be some tables. I don't think the table in the back of your book for statics does it, but I think double checking your math is going to be the most important way to check your work on this, because it's not like a reasonableness kind of check. Okay, so Iy equals 1.067 inches to the 4th. So we've got kind of the critical cross-sectional properties of this area. Area is going to come in handy when we're talking about the stresses due to an axial force on a member. The centroid is going to be important because eventually, even though here I told you to give me the moment of inertia about the x-axis and the y-axis, eventually we're actually going to start needing to get the moment of inertia about what we'll call like the x0 and the y0 axes, which are the axes that pass through the centroid. That's why the centroid is going to be important later on in strength of materials. The distance of a point of interest, let's say I care about the stresses at this point right here. The distance from the centroid is going to be a critical distance that we have to look at. And so that's why centroid is important. And then the moments of inertia, whether they're taken about the specific axis that I tell you, x or y, or they're taken about the centroidal axes, that's going to be an important part of calculating the stresses due to a moment acting on a cross section. So we'll look at both of those in a lot more detail in EAS 212. And then the final two values here are relatively easy to calculate. For part E, J, which is known as the polar moment of inertia, J is just simply equal to Ix plus Iy. So I'm not going to go to the trouble of plugging in those values. This is this value right here, 0.5714. This value right here, 1.067. Add them together, still in units of inches to the 4th. The other value is called the radius of gyration, in this case about the x-axis. Now the radius of gyration is important for calculating some buckling values for a column. Rx allows us to figure out at what vertical force would a column start to buckle. And so it's kind of this analysis right here. If I have a column like this and I'm pressing down on it, eventually it's going to buckle out to the side. It's not crushing, it's not yielding or anything else like that. And that value Rx is going to be a critical part of that calculation. Now fortunately, it's a very simple calculation. It's simply equal to the square root of Ix over the cross-sectional area. So it's a very easy calculation to make. And you can see if we're in inches to the 4th in the numerator, inches squared in the denominator, and I take the square root of that, I'll get inches as a result. So both important values, but computationally not very hard to calculate whatsoever. Rx is used for buckling. J is used for what's called the torsional stresses due to a moment about the axis of a member. So we'll look at them both in a lot more detail in EAS 212. but the calculation is not very rigorous. I would point out for the radius of gyration, there's also a radius of gyration about the y-axis, and maybe not surprisingly, is simply equal to the radical IY over A as opposed to IX over A.